Now, it would have been a bit more satisfying if I had done this slightly the other way around. So this is true and this is fine, but it would have been a bit more satisfying, let me see if I can use blue, if I had said that this one implies x is equivalent to b. Because then down here, I would have had a is equivalent to x, and x is equivalent to b, giving a is equivalent to b, giving that the equivalence class of a is equal to the equivalence class of b, which is the way around I had it. Now it doesn't really make any difference because we know that equality works both ways round, but it would have looked a bit more satisfying, I think, if I'd done it that way around, because then the thing that I was trying to prove, remember when you're trying to prove something, you start with something, here's that thing we started with, and we're trying to prove something, and here's the thing that we ended with. And it's much more satisfying if when you actually finish, the thing that you end with actually looks exactly the same as the one that you were aiming for. So that would have been better, I think. Anyway, that aside, we now know that if you have an equivalence relation, it divides up your set very nicely into these equivalence classes. So let's go back to our example of modular arithmetic and see what the equivalence classes give us in that case. Let's do arithmetic mod 5. I shouldn't have rubbed that out, should I? Let me put that back in again. The equivalence class of A is the set of all elements of S such that A is equivalent to X. So let's have an example. Let's do the integers mod 5. Okay, so in this case, the set on which we're taking our equivalence relation is the whole integers, right? And remember that A is related to B here if and only if 5 divides B minus A. So what's the equivalence class of 0? Well, what are all the numbers that are equivalent to 0 mod 5? Well, obviously 0 is equivalent to 0 mod 5, and then there's also plus or minus 5. Actually, I'm not going to write it like that. I'm going to put my 0 here, and I'm going to go 5, 10, 15, 20, and so on. And also minus 5, minus 10, minus 15, and so on in that direction. So it goes off in both directions. And the equivalence class is the set of all the integers equivalent to 0. So what about the equivalence class of 1? Well, if we start with 1 in the middle again, we get 1, 6, 11, 16, and so on. And then in this direction we'll get minus 4, minus 9, minus 14, and so on. I suppose I should put in the 21 here. And you'll note that all of these numbers are just 1 bigger than all of those numbers. So then, if we do the equivalence class of 2, we'll have minus 13, minus 8, minus 3, 2, 7, 12, 17, 22. Now you should probably press pause now and make sure you can write down the other equivalence classes. How many different equivalence classes are there going to be altogether? Have you done it? Well, there's going to be the equivalence class of 3, and the equivalence class of 4. So 3 is going to be 3, 8, and so on, in this direction, minus 2, etc. The equivalence class of 4 will have 4, 9, and so on, and in this direction, minus 1, and so on. But what's the equivalence class of 5 going to be? Well, the equivalence class of 5 is going to have 5 in the middle, and 10, 15, and so on, and 0, and minus 5. Now, it doesn't matter how the numbers line up with the numbers up there, right? But you can see that the equivalence class of 5 is going to have exactly the same numbers in as the equivalence class of 0. So this is the same as the equivalence class of 0. And the equivalence class of 6 what's that going to be the same as? That's going to be the same as the equivalence class of 1. Right? And so on. So there are only actually 4 different equivalence classes. 5. Bleh, there are 5 different equivalence classes. This one, this one, this one, this one, and this one, because all the others will be the same as one of those ones. And that's why when we're doing arithmetic mod 5, the only numbers we ever have to talk about are the numbers 0, 1, 2, 3, and 4. We could do modular arithmetic just using the numbers 5, 6, 7, 8, and 9, or if we were really strange, we could use the numbers 0, 6, 12, I've lost count. I need something mod 3. Right, so maybe I should write this down. This is why. So, to do arithmetic mod 5, we only have to use 0, 1, 2, 3, and 4. But we could use 5, 6, 7, 8, or 9. Or if we were really weird, we could just pick any old numbers as long as one was equivalent to each of these. So we could use 0 for 0, and then we could use 6, and then we could use 17, and then we could use 48, and we could use something that's equivalent to 4, 3,614. Which would work perfectly fine. It would just be very, very strange. Of course, none of us is very, very strange, so we're not going to do that. Weird. Now, the point is that it's much easier to write down these numbers than to write down the entire set of numbers equivalent to them. If we wanted to write down the entire equivalence class, it would take a really long time. So it's easier to refer to them by one chosen element, and these are called representatives. Equivalence classes. We just pick one to represent each equivalence class. It's a bit like if you were sending lots of schools to some kind of meeting of schools, you might just pick one person to represent each school there, and they would be, they wouldn't actually be the whole school, but they would be the representative of that school. So this is what we often do to make it more convenient. But the difference between equivalence classes and representatives of equivalence classes can be a bit confusing. So remember it like this, that you could pick these weird ones and that would have exactly the same effect, because really you're still just referring to the same equivalence classes, because these are all in the same equivalence class. Those are all in the same equivalence class. And so on. Of course, there's lots of other stuff in that equivalence class as well.